For decades, astronomers wondered what a comet from another star system would look like. Not in theory, not in simulations, but in reality. In 2019, for the first and so far only time they found out, its name was 2I Borisov. And unlike every interstellar object before or since, it gave scientists something they had never had before: time, clarity, and proximity. This was not a fleeting mystery. This was an interstellar visitor we could actually study, up close. Before Borisov, interstellar objects were surprises. They appeared suddenly, moved fast, and left before we fully understood what we were seeing. That was the case with Oumuamua in 2017, the first known interstellar object. By the time telescopes turned toward it, it was already on its way out. But 2I Borisov was different. It was discovered early. It was active. And it behaved like a comet. That combination changed everything. On August 30, 2019, an amateur astronomer named Gennady Borisov detected a faint object moving through the sky. At first, it looked ordinary, but orbital calculations quickly revealed something extraordinary. The object was traveling too fast to be bound to the sun. Its path was hyperbolic. It was not from here. Within days, astronomers confirmed it. 2I Borisov was an interstellar comet, the second confirmed interstellar object ever observed, and the first of its kind. Unlike Oumuamua, Borisov showed a clear coma. Gas and dust surrounded its nucleus. A tail formed as it approached the sun. This was immediately significant, because it meant Borisov behaved like comets we already understood, just not from our solar system. That made it familiar. And familiarity is powerful in science. Borisov passed through the inner solar system slowly enough and brightly enough for telescopes to track it in detail. Not just for days, but for months. Observatories around the world coordinated observations, including the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, large ground-based observatories across multiple continents. For the first time, scientists could measure composition, track activity over time, observe structural changes. This wasn't a snapshot, it was a study. As data came in, one thing stood out immediately. Borisov was rich in carbon monoxide, much richer than typical solar system comets. That detail mattered, because carbon monoxide sublimates at very low temperatures, which means Borisov likely formed far from its home star in a cold, distant region, just like the outer edges of our own solar system. That was a profound discovery. It suggested that other star systems build comets the same way we do. In many ways, Borisov was comforting. It followed the rules. Its chemistry made sense. Its activity matched models. Its behavior was predictable. After the confusion surrounding Oumuamua, this was a relief. Borisov didn't challenge physics. It confirmed it, and that confirmation was just as important as any anomaly. As Borisov approached the sun, it became more active. Jets of gas erupted from its surface. Its tail lengthened. Brightness fluctuated. Then something else happened. The comet began to weaken. Observations showed changes in brightness that suggested fragmentation. Its nucleus was breaking apart. Scientists were watching an interstellar object age in real time, and eventually Borisov began to fall apart entirely. By late 2020, Borisov was fading. Its activity dropped. Fragments dispersed. The comet continued on its hyperbolic path outward, never to return, but the data remained. Hundreds of observations, spectral measurements, thermal models, a complete record of an object born around another star. 2I Borisov answered a question scientists had been asking quietly for decades. Are other solar systems fundamentally different from ours, or are they built from the same basic ingredients, shaped by the same physical rules? Until Borisov, there was no clear way to know. Models suggested similarities. Simulations hinted at overlap, but there was no direct evidence. Borisov changed that. When its chemical makeup was analyzed, what scientists saw was not exotic or unfamiliar. It was recognizable: water vapor, carbon-based compounds, carbon monoxide in unusually high abundance but still within a framework we understood. In other words, Borisov looked like a comet from home. That matters more than it sounds, because it suggests that the processes that formed our solar system, the collapse of gas and dust, the formation of icy bodies in distant stellar outskirts, may be common across the galaxy. Not rare, not exceptional, common. That realization reshapes how we think about planet formation, about chemistry beyond the sun, and about how often familiar materials might exist elsewhere. It tells us that our solar system may not be an outlier. It may be one example among many. Since Borisov's departure, astronomers have been watching carefully. Sky surveys have improved, detection algorithms have become more sensitive, telescopes are scanning more of the sky more often, and yet nothing quite like Borisov has appeared again. That isn't surprising. Interstellar comets are extraordinarily difficult to detect. They are faint, they move fast, and they do not announce their arrival. Most pass through the solar system unnoticed, far beyond the reach of our instruments. Borisov was different because of timing and geometry. It approached from the right direction, at the right brightness, at a speed that allowed extended observation. That combination is rare. It may take years or decades before another interstellar comet passes close enough, slow enough, and bright enough to study in comparable detail. Which makes Borisov's data set uniquely valuable. It is not just an observation. It is a reference point that may stand alone for an entire generation of astronomers. Borisov represents the baseline, the control case. It shows us what a normal interstellar comet looks like when everything behaves as expected. Its structure made sense. Its chemistry followed known rules. Its evolution matched established models. And that clarity turned out to be essential. Because once you understand the ordinary, you can recognize the extraordinary. Discoveries like Oumuamua and later, 3I Atlas stand out precisely because they deviate from what Borisov showed us. Without Borisov, those anomalies would be harder to define. With Borisov, we have context. We know what normal looks like when material from another star system passes through ours, and that makes every deviation meaningful. 2I Borisov did not arrive with mystery or spectacle. It did not challenge our understanding of physics. It did not demand new theories. It arrived quietly, behaved predictably, and left behind something far rarer than shock or surprise. It left behind understanding. It was the only interstellar comet we have ever studied up close. And in doing so, it reminded us of something profound. That while the universe may be stranger than we imagine, it may also be built from familiar foundations, repeated across countless star systems we will never visit. Every once in a while, something from another star system passes through our sky. Most will go unnoticed. But when one doesn't, when one gives us time, clarity, and data, we have an obligation to pay attention. Subscribe to our channel. Because the next interstellar visitor may not look like Borisov. And when it arrives, understanding the last one may be the only way we recognize what makes the next one different. What we've learned so far is only the context. The real understanding lies ahead.